Can you all hear and see my screen?
Yes.
Thank you. Thanks for the introduction, and thanks for organizing this wonderful conference. My name is Weipeng WU from the University of Delaware. Today, I will talk about manipulation of terahertz spectrum using microfabricated magnetic heterostructures. So let's start with a brief introduction to terahertz technology. So the terahertz frequency falls in the gap between optical and the radio frequency, which in particular, we are interested in this region. There are various of interesting phenomena and applications in this frequency range. For example, the bioscanner, the interchip wireless, and mobile phones. So how can we generate terahertz? Conventionally, there are two standard terahertz sources. One is photoconductive antenna, PCA. The other one is nonlinear crystal. Despite of their wide usage in reality, there are drawbacks of those two sources. For PCA is the complexity in engineering terahertz emission, and they tend to break easily. And for nonlinear crystals, they are relatively expensive, and they really require intense pump pulse because they're making use of nonlinear effects. And for crystals, oftentimes they have high frequency cutoff. Overall, those two terahertz sources imply only the charge property of an electron. However, there are more about an electron, right? Like the spin. So we might think, can we create an alternative, inexpensive, reliable broadband terahertz emitter based on spins of electrons? The answer is yes. Over the past decades, it is found out that when the ferromagnetic heavy metal bilayer is excited by femtosecond laser pulses, we can detect a terahertz radiation from the other side of a sample. How does this process happen? Let's break it down into details. Here, I'm showing a schematic band structure of iron platinum bilayer structure. As you can see that near the Fermi level of iron layer, there are uneven number of spin up and spin down electrons. And when we shine light the femtosecond laser pulses on this structure, more spin up electrons are excited than the spin down electrons. So which leads to an ultra fast spin current in the ferromagnetic layer. And this spin current is diffused into the adjacent platinum layer, and due to spin optocoupling and the inverse spin Hall effect, this spin current is converted to a transverse charge current, which finally leads to a terahertz transient. And it is found out that the generated terahertz signal has comparable signal strength and is broadband. Last but not least, they are less costly and easy to fabricate compared with conventional terahertz sources. So here I'm showing a time trace of terahertz signal measured using a time domain terahertz spectroscopy. This is a signal from a reference iron platinum bilayer. And if we do fast Fourier transform to this time trace, we can get the terahertz spectrum in frequency domain. So we demonstrate that we can measure, create and measure time terahertz signal from this layer. But what about next? Maybe we want to manipulate the terahertz spectrum and try to expand the functionalities of terahertz radiation. But the question is how? So we borrowed some ideas from classical optics and developed a simplified multi-slit interference model. Here, the monochromatic planar wave is instant on a screen with multiple slits, and then forms an interference pattern on the optical screen at a distance. So, and the intensity distribution on the screen can be numerically described. Now let's recall, the terahertz radiation is a sub-millimeter wave which if we choose the proper slit width and slit separations, we might also be able to see terahertz interference on the screen, right? So we run a simulation in this scenario where we keep the separation of the slits at 510 micrometers and vary the slit width. This situation is equivalent to a stripe sample where we keep the separation of stripes at constant distance, and then we vary the stripe width. And here is what we the simulation results. As you can see that at the chosen frequency 0.5, 1 terahertz, and 1.4 terahertz, by increasing the stripe width from 200 to 300 to 400 and finally to 490 micrometers, we can see a modulation to the intensity distribution on the detector. So this will later be reflected on the terahertz spectrum we could observe. And then we use the reference film, the spectrum of the reference film as an input spectrum, and calculate the spectrum of different microstructures. As you can see that this is, we can see the terahertz spectrum is truly modulated by this kind of microstructure. And as we vary the stripe width by, or we change the microstructures, we can see a modification to the terahertz spectrum. Overall, we see the change of terahertz bandwidth over here, and then a moving of the peak over here. So to solidate our simulation result, we fabricated samples with exactly the same dimensions as mentioned before, separation distance 510, and vary the stripe width using optical lithography and magnetron sputtering. And then we measure the sample using a time domain terahertz spectroscopy system in this experimental configuration. And in the experiments, we magnetize the sample along the stripes and then detect terahertz radiation with vertical polarization, because due to the inverse spin Hall effect, the terahertz pulse is perpendicular to both the magnetization as well as the spin current direction. And here is what we found. So you can see that here I'm showing the control film, experimental data, and the simulation. You can see that the simulation follows quite well with our experimental data. And they both show modification to the control film spectrum. And what about we increase the stripe width, which by means we change the microstructures. As you can see that as we increase the stripe width, the modification to the reference film moves slowly to from higher frequency region to low frequency region, which is what we would expect, because low terahertz frequency means longer wavelengths, which will interference more for larger stripe width. So from this result, we can conclude that modulation by microstructure is experimentally detected and explained. To summarize my talk, we can see that terahertz emission from the microstructure magnetic heterostructure is experimentally confirmed and measured using a time domain terahertz spectroscopy system at femtosecond times resolution. And then we can see terahertz spectrum is explained in terms of a simplified multi-slit interference model. Finally, the terahertz spectrum verified that manipulation of terahertz spectrum can be realized by carefully designed magnetic heterostructures. And finally, if you are interested in time domain terahertz spectroscopy technique and you are interested in terahertz photonics, I would like to refer you to our recent published tutorial article on arXiv. And finally, This work was supported by Dashwood Science Foundation, and we would also like to thank Argonlash Lab for the fruitful collaborations. Thank you all, and I'm glad to take any questions.
Thank you, Weipeng. This talk is now open for question.
Okay.
Is there any question from the audience? You can use the reaction and raise hand. Okay, I have one question regarding the future direction. So
please go ahead.
What do you want to do next? Like, you showed the modulation by showing the microstructural manipulation. So what's next? So
actually, there are more to explore. For example, in terms of material systems, we can try different material systems. And on the other side, you can see that now we are using microstructures to modify the terahertz spectrum. Basically, we are changing the terahertz spectrum. On the other hand, maybe in the future, we can use microstructures to change the chirality, maybe the polarization of the terahertz. That's also possible. Actually, there are already papers showing that they can use microstructured magnetizations to change the polarization of the emitted terahertz. Yeah.
Okay. What kind of material properties you are going to explore if you want to change the material?
Basically, because if you just look at the mechanism of the generation of terahertz, see here we want a spin current source, right? And then we want to actually convert spin current to charge current. So basically, we are playing around. We can play around with the spin current source as well as the spin to charge converter. Like here we is showing as platinum as the spin to charge converter. Later we can probably use any material with a larger spin Hall angle. That would be like, yeah, a possible direction.
Okay. Okay. Thank you, Weipeng. Any other question for Weipeng? Okay, if not, thank you, Weipeng. We'll move to the next talk. Our next talk is from Zulfidin KHODZHAEV from Oklahoma State University. I'm sorry if I mispronounced your last name.
Zulfidin KHODZHAEV, but thank you for the introduction. Can I share my screen now?
Yes, go ahead.
Hello, everyone. So this is Hopfion Dynamics in Chiral Magnets presentation. I am Zulfidin KHODZHAEV, a PhD physics student from Oklahoma State University. So we'll be together for the next 12 minutes. So now I want to give you an outline of what I will be going to discuss here. So we did the resonance spin precession dynamics of a Hopfion and chiral magnet micromagnetic simulations. So first I will try to go over the background for the audience who are not familiar with the Hopfions. And then I will show you the method that we used to get the results. And of course, I'm very excited to share the results we have. Now, a little bit of background. A Hopfion is a knot on a three-dimensional torus. And the knot basically defines the classification of the Hopfions. For example, here, this is what is called Hopfion charge 1, Hopfion charge 2, and Hopfion charge 3. They basically correspond to knot 3, 2, 1, respectively. And the mathematical description of a Hopfion charge is basically an integration of these two vectors. We've used this equation throughout the simulations just to make sure that we have the right, or we have a Hopfion indeed. So this is basically, sometimes it's called Hopfion index, Hopfion number. So this is to verify. Now we have two types of Hopfions. One of them is block Hopfion in this image. This is the middle layer of the block Hopfion. It's created using what is called bulk DMI. And the second type is anneal Hopfion. And this is an image of a middle layer of an anneal Hopfion. And this is created using the interfacial DMI. Anneal Hopfion is something new. The first time it was discussed in 2019. So first, I will go over the block Hopfions, and then we will continue with the anneal Hopfions. Now, why this is important? Researchers have been trying to create and observe experimentally a Hopfion in magnetic multi-layer systems. For example, in this paper, in iridium, they've used iridium cobalt platinum multi-layer to observe the Hopfions. But as you can see, the techniques and the devices they use, they may not be always available for all the researchers. So that is a barrier. So this is where our research comes in. When imaging is not possible, researchers can use our method to identify three-dimensional topological spin texture of Hopfions in chiral magnets. And of course, all of these eventually will lead to the low current manipulation for future power efficient memory applications. In other type, you've heard Skyrmions. So Hopfion is a new field, hopefully. Now, so let's go over the method. So first, we've introduced the geometry of the Hopfion and Hopfion charge. So we wrote the initial ansatz. We've done all our simulations using Mumax 3, if that helps. And then we identified the ground state of the Hopfion in the chiral magnet. Then this initial ansatz, the ground state of the initial ansatz ends up to be a Hopfion whenever we used a demagnetizing field. But there is another ground state of the initial ansatz. It's the monopole anti-monopole pair. So whenever there is no demagnetizing field, this ground state of the initial ansatz ends up to be MAP. Now, this demagnetizing field, sometimes it's ignored or it's not discussed in the papers. So it's very important to include this demagnetizing field because it keeps the Hopfion's stability. So it keeps it more stable. It makes it more stable. And then we've excited the Hopfion with magnetic pulse, and we analyzed the resulting precession frequencies and spin wave modes. This is where the researchers can use in their experimental work. And then, of course, we varied the external magnetic fields that led us to the resonance frequencies. Now, let's look at the resonance frequency profile. So in order to get this, we've used 0.1 nanosecond magnetic pulse. We recorded magnetization for 200 nanoseconds, and by taking Fourier transform of the spin precession, we plotted the spin resonance profile. So this is the block Hopfion, and this is the frequency resonance profile for -15 millitesla. Of course, we did it for the other fields too, and this is what we have. Remember, this is logarithmic plot. So we've observed that whenever you increase the magnetic field, the amplitude or the main frequency resonance shifts to the right. And this was the case for the new Hopfion 2, which I'm going to show in the next slides. Now, just to look at the spatial distribution of the resonance amplitudes. So for the lower frequencies, we've observed that there's more rotation of the Hopfions. At higher frequencies, we have more breathing close to the center of the Hopfion. And of course, as you can see, whenever you go to the top layer, you see that torus and the knot rapids. So let's continue with the Neal Hopfion. Now, for the Neal Hopfion, whenever we applied external magnetic fields, the geometry of the Neal Hopfion changed from circular to more square. But it is still a Neal Hopfion because we checked the Hopfion charge using that equation. The Hopfion charge was still close to 1 in this case too. So it's just some characteristic of the Neal Hopfion that we observed, and this happened around minus 300 millitesla. Now, just to show you more the frequency profile of the Neal Hopfion. So remember, I was showing you the logarithmic, just to show you how it looks like without logarithmic scale. As you can see, the amplitudes are actually much higher, right? And it goes down. And you can see clearly the shift shift to the right whenever you increase the magnetic fields. So it's the same for the Hopfion too. Whenever we increased the magnetic fields, we saw the amplitude shift to the right. Now, just to talk more about the Hopfions in this case, we've seen the same phenomenon. Whenever the frequency is low, we see more rotation of the Hopfions, and whenever we at the higher frequencies, we see more breathing close to the center of the Hopfions. And this is the case when it's circular or it's square. So I'm talking about the Hopfions. And the first one is for -60 millitesla, and this was for the -180 millitesla. And thank you for your attention, and I'll be waiting for your questions.
Thank you very much. Are there any questions from the audience? You can raise your hand. So if not, Christina has a question.
Yeah, thank you for the talk. So have you applied fields on directions in the plane?
So the directions we've used is in Z direction in this case.
So
it's
then that would resemble the breathing mode, like, because with the understanding we have from Skyrmions is that if you apply out of plane, you activate the breathing mode. But if you apply in plane, you have other modes. Do you expect something similar or?
So for now, that's at least what we assume, that what we see is a breathing mode for the higher frequencies. Of course, I can get back to you on this question if you email me or if we keep in touch. Thank you.
Thank you.
All right. Are there any other questions from the audience? If not, thank you very much for the talk. Our next speaker is Maria SCHÖNHÖBEL from the University of Basque Country in Spain. Let me find you here.
So hello, everybody. Can you see my screen? Okay, hello, everyone. I'm Maria SCHÖNHÖBEL. I'm pleased to present this talk, which is about magnetoelectric effect in composite of piezoelectric ceramics and nickel manganese gallium ferromagnetic shaped memory alloy design and measurement. Here are my co-workers, and I'm from University of Basque Country. This work was done there. And so multiferroic materials are of great interest because they exhibit at least two ferro orderings in the same phase. So the presence of these orderings in a single phase leads to magnetoelectric coupling. So single multiferroic materials have difficulties device application due to their low Curie temperature, which is below room temperature, and with coupling between electric polarization and magnetization. So alternatively, composites of magnetostructive terphenol, like terphenol and piezoelectric phase possessed a stronger affected string-mediated magnetoelectric coupling. So magnetoelectric coupling is characterized by magnetic field-induced electric polarization and electric field-induced magnetization. The first one means polarization can be switched by a magnetic field, and the second one, it's like magnetization can be switched by an electric field. So these remarkable characteristics make them suitable for different applications, such as magnetic field sensors, information storage devices, and energy harvesters. So in this work, we designed a setup to measure the magnetoelectric effect of a bulk composite. So this bulk composite was composed by a magnetostricted phase, which was a ferromagnetic shaped memory alloy of single crystal nickel manganese gallium, and the piezoelectric phase was lead zirconate titanate ceramics. So what we did first was made a mechanical training of the single crystal. Then we prepared the composite, and then we designed the setup, and finally we measure and analyze the composite response. So we start with the mechanical training of the nickel manganese gallium single crystal, and we followed this route that you can see here. And after that, we cut a piece, which you can observe in the photo, and we apply a magnetic field parallel, perpendicular and parallel to these lines, which are the twins. So after that, we measure the magnetic, we apply different magnetic fields from 0.2 Tesla up to 1 Tesla, and we measure the deformation and then the strain, and we obtain strains up to 4% for magnetic fields larger than 0.4 Tesla. So here we can see the temperature dependence of magnetization after cooling the single crystal from 385 Kelvin, and then we heating from 285 to 340 Kelvin. And from here, we can see the single crystal nickel manganese gallium undergoes a martensitic phase around 300 Kelvin, which means the single crystal is in a martensitic phase at room temperature. So once we confirm that, we prepare the composite by joining the ferromagnetic shaped memory alloy and 2 piezoelectric plates mounted on a cylindrical sample holder, as is shown in this photo. It is important to join the 2 plates in the best possible way to transmit the mechanical stresses, taking into account that the piezoelectric is deformed by a compression mechanism and not by shear stress. So finally, the composite is fixed with a screw, which is here, that it's along the axis of the composite. So the sample holder was placed between the poles of an electromagnet. Then, to measure the magnetoelectric voltage, a DC magnetic field produced by this electromagnet, and an AC field which was produced by these Helmholtz coils were applied, and thereby deforming the ferromagnetic. Here we have the composite. So when we apply the magnetic fields, the ferromagnetic shaped memory alloy is deforming, and this produces a compressive stress on the piezoelectrics and plates, those generating an AC signal, which is detected with the lock-in amplifier, and the other lock-in was using to determine the voltage induced in this little surge coil, which is here, which was detecting the current, and with that we can determine the AC field. So here we have the magnetic field induced voltage in the piezoelectric as a function of frequency between 1 and 10 kilohertz for different magnetic fields from 0 to 1.1 Tesla, and keeping the AC magnetic field at 80 ampere per meter. So both the AC and DC fields were applied parallel to the axis of the composite. So apparently the electric response increases linearly with frequency for any magnetic field, and the behavior is very simple. So however, if we look more closely, we realize that there are small differences for different magnetic fields. So one way to calculate the difference between the voltage at an H and at 0 field However, in this way, the noise at zero field, which is at zero field, is the blue plot. So this noise, it's like reflected in the other plots. So what we did was to determine the difference between the voltage at H and the linear fit at H equals 0. And in this way, we observe the behavior is not linear and it is concave up. So, and the new response is different from different magnetic fields, as you can see from here. So here we are comparing the electric response when the field is applied parallel and perpendicular to twins. So from here we can see in a parallel case. So the change is smooth and continuous. In the perpendicular case, we can see a jump in the behavior when magnetic field is on. So this is a 2D sketch of the composite mounted in the sample holder. So here we have the two piezoelectrics and the first shape memory alloy. So during the process, the ferromagnetic shape memory alloy, it's under compression stress, which can be changed with the screw, at the same time modifying this distance. So at the bottom, the plots show the slope of linear fits, different magnetic fields. In the parallel case, as you can see, the slope is not changing. It's like constant with the magnetic field, but it's changed with the compression. And the slope changes. For example, in the perpendicular way, when the magnetic field is larger than 0.7 Tesla. Also, the response is larger than in the parallel case. So next step was heating up the composite up to 37 degrees Celsius by using a small coil as a furnace. So here you can see the coil. Inside is the composite. And we analyze the magnetoelectric coefficient, which is this differential, as a function of frequency and magnetic field at room temperature and at temperature above martensitic transformation temperature. So in both cases, we observe planes where magnetoelectric coefficient are between 27 millivolts per centimeter Oersted, and also a magnetoelectric coefficient being smaller, both frequencies and flow fields. In any case, the magnetoelectric response is larger at room temperature, as you can see from the color map. So when fitting the experimental values using this equation of the plane, we observe the important changes are due to the coefficients associated with frequency. So at room temperature, the magnetic field coefficient is approximately one order of magnitude larger than that of the composite when temperature is above the martensitic temperature. So when we observe deviations of magnetoelectric coefficient with respect to the fitting of the plane as a function of frequency and magnetic field, in both cases, the largest deviations are found for frequencies below 2 kilohertz. So since we are analyzing the deviations, we are amplifying some effects. So between 3 and 4 kilohertz, we have instrumental error. From color map, the deviations are smaller when the temperature is above martensitic temperature. So with this, I conclude my talk. So let me summarize. So the magnetoelectric response depends on the compressive stress, which the ferromagnetic shape memory alloy is subjected. Regardless of the compression stress, the magnetoelectric response shows the same form. Globally, this differential is practically flat with an almost linear growth with frequency and a negligible change with respect to the DC field. And the magnetoelectric response deviates from this behavior with a curve that shows concavity up. So magnetoelectric coefficient and deviations are smaller when ferromagnetic shape memory alloy is heated and for frequencies between 1 kilohertz and 10 kilohertz, the magnetoelectric response is between 30 and 210 millivolts at room temperature. So thank you, everybody. And
Thank you, Ana Maria, for the nice talk. Is there any question from the audience for this talk? Oh, there is one question from Purnima.
Oh, yeah, I have a quick question. You showed that there's a different behavior depending on whether the field is applied along the twins or perpendicular to them. Is one of these behaviors like desired or?
yeah, I mean, apparently,
which one is preferable?
yeah, I mean, apparently we are having best responses when we apply the magnetic field perpendicular to twins, but when we also try to do analyze the data better, try to do a better analysis, we realize that here as the compression, it's even more important. It's being more important than magnetic field. So to disclosure that, we need to do another test before I can assure something.
Okay. And are you cooling, like when you grow the materials, are you applying a field when you like cool them down or anything? Or are they, you had some very specific cooling procedure. So
let me see. But in which part? In this one?
when you actually grow the materials.
Sorry. In which part is that? Yeah, when I was analyzing the ferromagnetic shape memory alloy, you mean? Sorry.
I'm asking, I think at the very beginning when you're talking about how you
this one, right?
grow the materials. I think it's like the previous slide from this.
Yeah.
Here. Are you cooling these in a magnetic field, or this is just?
Okay. No, with no magnetic field. It's just like cooling to 200 in a furnace, regular furnace, and then after that we cooling down to room temp. I mean, after that we remove it. We remove the crystal from the furnace, and then we cooling down, but at the same time under a constant compressive load, approximately of 10 megapascals. But no magnetic field in that stage.
Okay, thank you.
Okay.
Thanks, Ana Maria, for this talk. We will move to the next talk. Our next speaker is Jonathan Gibbons. He is from University of Illinois Urbana-Champaign. Jonathan, go ahead, share your slides.
Great. Thank you very much. Can everybody now see my slides and hear me?
Yes.
Great. Awesome. Thank you very much. I'm Jonathan Gibbons. I'm a postdoc working with Axel Hoffman at the University of Illinois at Urbana-Champaign via the Quantum Materials for Energy Efficient Neuromorphic Computing, EFRC. Today, I want to talk to you about some large exotic spin torques that we've observed in antiferromagnetic iron rhodium. And before I do that, I want to thank all of my fantastic collaborators who have made this work possible. So I want to start by giving a little bit of background about what I mean when I say exotic spin torques. So in a highly symmetric material, like say platinum, the crystal structure of the material is very symmetric. And so when we talk about spin orbit effects that can generate spin currents and spin transfer torques, like the spin Hall effect, in such a material, the geometry of the spins that we can generate is limited by the high symmetry of the material. So these symmetry axes forbid certain kinds of torques. So torques that are ordinarily forbidden in high symmetry materials are called exotic torques. And various things can break this symmetry, reduce the symmetry of the material. For instance, crystal asymmetries can do that, but relevant to this talk, magnetic ordering can also do that. So that's been predicted and observed for ferromagnets. and also been predicted and observed for antiferromagnetic materials. And potentially this allows us to get spin polarizations that are ordinarily disallowed and novel geometries of torques. In particular, we can get spin polarizations that are parallel to the magnetic ordering or perpendicular to the magnetic ordering are the most commonly allowed spin torques in these systems. So we investigated antiferromagnetic iron rhodium. It's a 50-50 alloy. So we chose this material because it has a sizable anomalous Hall effect, which indicates large spin orbit effects. And so we thought it might have a large spin torque efficiency. And it has antiferromagnetic ordering that may allow for exotic torques. And moreover, because it has a transition between antiferromagnetic and ferromagnetic ordering right around room temperature, that potentially allows for the manipulation of the magnetic ordering and also for it to be prepared into an antiferromagnetic state or ferromagnetic state at room temperature. So in order to get at this, we created a stack with iron rhodium. That's the spin source layer. The current travels through that and generates spin current. And then there's a copper spacer layer that isolates the two layers magnetically. And then we have a permalloy sensor layer, which has the torque exerted on it from these spin currents and through which we see the size of those torques. So our first measurement technique to get at this was spin torque ferromagnetic resonance. This is an RF technique. So you apply an RF current through your device that generates an RF spin current, which exerts an RF torque on the permalloy, the sensor magnetic layer. It drives that layer into precession, and that precession creates an oscillating anisotropic magneto-resistance. And when the resistance is oscillating at these RF frequencies, you have a resonance between that and the applied current that generates a DC mixing voltage, which we can measure via a lock-in. And this DC mixing voltage is resonant as we sweep the field and thus the precession frequency of the magnet through the applied frequency direction. So by sweeping the field, we can measure this resonance. And the key information that you should take away from this is we can measure this mixing voltage. We can fit to it to extract the Lorentzians that make up it. And our signal is a combination of a symmetric Lorentzian, which is driven by anti-damping torques and other similar things, but typically anti-damping torques, and an anti-symmetric Lorentzian that's driven primarily by Ørsted torques, typically. And so by looking at the size of these terms and fitting to the data, that the mixing voltage data we get, we can extract the size of the anti-damping torque. So we performed these measurements on our iron rhodium copper permalloy stack at room temperature and several other temperatures. And as you can see, the symmetric component is very, very small, which indicates that there's a very small spin torque efficiency. It's highly temperature dependent. It increases by a factor of about 3.5 from 300 Kelvin down to 170 Kelvin. But because it's so small, this doesn't seem that interesting. But this isn't the whole story. We can use other measurement techniques to try and probe what sorts of spin torques might exist in the system. So we did some DC biased spin torque ferromagnetic resonance, which is another STFMR technique. So when you extract the symmetric and anti-symmetric components of this line shape, you can also extract the line width. And the line width of the ferromagnetic resonance is related to its damping. So it grows linearly as the damping grows. And so it's possible to view the anti-damping effects of an anti-damping torque, that is changing the damping of the material effectively, through looking at the change in line width as we apply an anti-damping torque to the material. So in fact, the line width ends up being linear with the spin torque efficiency and the applied current. So because of this, we can do an experiment where we measure spin torque ferromagnetic resonance as we did before, but at the same time, we apply a DC charge current through our device. This DC charge current creates a DC spin current, and that DC spin current changes the effective damping of the permalloy and therefore changes its line width. So then we measure this for a bunch of different currents ranging from -10 to 10 milliamps. We fit to it, we extract the line width, and then we can do a fit to that line width that's linear in the applied DC bias current. And from that, we can extract the spin torque efficiency. So the result of that, we see enormous spin torque efficiencies. They're around a little over 90% at 300 Kelvin, and they're above 300% at 170 Kelvin. These are very, very large, but they also have very similar temperature dependence. They increase once again by a factor of about 3.5 from 300 Kelvin down to 170 Kelvin. So it seems like these could be from the same effect, but they appear to be a little bit contradictory. So in order to resolve this, I need to talk a little bit about anti-damping torques and their geometry. So an anti-damping torque looks like m cross sigma, where sigma is the spin polarization of the spins that are incident on the magnet, and m is the magnetization direction. So there are two main geometric cases for this. You can have a spin polarization that's perpendicular to the magnetization, in which case the cross product here is very large, or you can have a spin polarization that's parallel to the magnetization, in which case the cross product is 0. So I'm going to talk about each of these cases individually. I'm going to start with the spins perpendicular to the magnetization. So in this case, m cross sigma is large. As you can see, the blue vector in the middle here is m cross sigma when the spin polarization is in the y direction, as you'd expect for an ordinary spin Hall effect. M cross sigma is large and out of plane, and m cross sigma is perpendicular to the magnetization and in plane and large. So this torque, a torque in the direction that the anti-damping torque is here, wants to pull the magnet away from its equilibrium position, which is going to drive it into precession. So we deflect the magnet, we drive precession. If this is an RF torque, this will drive your resonance. So in fact, this is the component of the spins that we're seeing when we measure the ordinary STFMR. We're measuring the components with spin perpendicular to the magnetization, because that's what drives resonance. Now, if the spins are parallel to the magnetization, on the other hand, m cross sigma is 0. So ordinarily you'd get no torque, except if the magnet is already precessing. If the magnet has been kicked away from its equilibrium position, m cross sigma is non-zero. It's a little bit small, but you can see the blue arrow here is what you get for m cross sigma. The spin polarization can have a cross product with the magnitude of the oscillation. And the end result is, if you apply a DC current and you get a DC spin torque, the torque rotates as the magnetization precesses, because the oscillation magnitude or the oscillation is rotating. So the torque is rotating such that it always either supports the precession of the magnet or it opposes the precession of the magnet. So it either works as a damping and damps away these oscillations, or it opposes the damping and decreases them. And so this is an anti-damping torque that changes the damping of the material. But this is only sensitive to spins that are parallel to the magnetization. So it turns out that when we measure the first technique, the ordinary STFMR, we're only measuring the component of the spin polarization perpendicular to the magnetization. And when we measure the DC bias STFMR, we're measuring the component of the spin polarization parallel to the magnetization. So what does this tell us? Well, it says that we have a very, very large spin torque efficiency, and one that where the spin polarization is parallel to the magnetization of the permalloy. So what directions are all of these things in? Well, for this experiment, for STFMR, you apply a field at a 45-degree angle to your underlying devices. So we expect the field to be saturating the permalloy, and therefore, since we know the spin polarization is parallel to the permalloy magnetization, we then imagine that the spin polarization is in that direction as well. Now, these are grown on MgO substrates, and MgO's crystal axes are, the devices are grown parallel to one of the MgO crystal axes. But when you grow iron rhodium, its crystal axes orient themselves at a 45-degree angle, which actually puts one of the iron rhodium crystal axes parallel to where we think our spin polarization is. And in fact, the iron rhodium magnetic ordering likely also follows one of the directions of the crystal axes. So we think that our spin polarization then is either parallel to or perpendicular to the magnetic ordering direction. So we believe that it's likely set by the magnetic ordering. In order to further confirm our results, we also performed second harmonic Hall measurements to try to extract the exact angular dependence of our signal and confirm the size of our spin torque efficiency. So these are second harmonic Hall measurements specifically for an in-plane magnetic sensor layer. So for this technique, it's the analog, the DC analog of spin torque FMR. So you apply a current, that current generates a torque. The torque causes a rotation of the magnetization, and that rotation changes the magneto-resistance of the material. And then at the same time, you detect the Hall voltage. And so in fact, we're talking here about the Hall magneto-resistance. So we detect the Hall voltage, and we can detect that rotation of the magnet as a change in the Hall voltage. And then once we're detecting the signal, we can rotate the magnetic field. And by rotating the magnetic field, we rotate the magnetization direction. And the torque, since its size is m cross sigma, the torque is expected to change as we rotate the magnetization. And so we can see that angular dependence and fit to it in order to figure out what the direction of the spin polarization sigma is. And you can also write out what the overall signal looks like that you're fitting to with the spin polarization components X and Y here that you can fit to them. So we fit to it assuming this 45-degree angle, what we saw from the spin torque ferromagnetic resonance, we fit assuming that angle. And here's our data as we sweep the angle. This is a microvolt voltage. And the fit works very, very well. So from this, we conclude that we're at least close to, if not exactly, at the 45-degree angle spin polarization that we saw from spin torque ferromagnetic resonance. And so then what about the size and temperature dependence? So at room temperature, we see a spin torque efficiency of about 60%, which is a little bit smaller than we saw from spin torque ferromagnetic resonance, but it's still quite large. And then once we cool down to 170 Kelvin, we see a spin torque efficiency of 160%, which is still very large, but once again, a little smaller than what we saw from spin torque ferromagnetic resonance. But this does confirm our large degree of temperature dependence, our perceived exotic nature of our spin torque, and also that we're getting very, very large spin torque efficiencies. So in conclusion, we've seen an exotic spin torque, one that wouldn't ordinarily be allowed for spin Hall effect in highly symmetric materials. And we've seen a spin polarization that's either parallel to or perpendicular to the magnetic ordering iron rhodium, which means it's probably the magnetic ordering defining the direction. And we've seen a spin torque efficiency that can be as high as over 300% at 170 Kelvin and over 90% at 300 Kelvin. Thank you very much for your time.
Thank you very much for the talk. I'd like to open this talk for questions. A reminder, you can use the reaction and raise your hand. So while we're waiting for questions from the audience, I have a question in regards to your the initial DC bias experiments.
Yes.
So you have these two plots of the change in line width for positive field and negative field. Is it just my eyes, or are those slopes different? And if so, what does that mean?
Yeah, the slopes are different. So there are some schools of thought on why this happens. It's thought that this could be a heating effect, but you see this fairly regularly in this measurement, that often the slopes are different. And the way we've done this is dealt with this is we averaged the two slope directions. And in fact, we have error estimates that include the difference in the two slopes in the error estimate. Which I can also bring up our results after error estimates are shown here.
Okay. And my other question is, so when you're doing the STFMR measurements, you mentioned that you want to apply your field along the iron rhodium crystal axes. Is there any difference if you change the orientation of your pattern on your sample? So if you're instead applying the current along the crystal axes, or does that matter at all?
So we've done some of this, and there were differences, and it was, so the growth process for iron rhodium can be a little bit finicky at times. So devices in different positions can give you different results, and we're currently working on trying to figure out what the differences are that are due to devices in different locations versus angles. And we can say that there's clearly a difference by the angle at which we've patterned the device, but we're not clear on exactly what it is yet.
Okay, thank you very much. Are there any more questions from the audience? Not, we can thank you for your talk, and we can move on to our next speaker, who is Mojtaba Taghipour KAFFASH from the University of Delaware in the United States. Let me unmute you. And you can start sharing your slides.
Hello, thank you. Can you hear me?
Yes.
And you can see my slide. Great, thank you. Hi everyone, welcome to my talk. My name is Mojtaba Taghipour KAFFASH from University of Delaware. Today, I'll be presenting the results from our recently published paper in APL with the title of Observation of Mode Splitting in Artificial Spin Ice, a comparative ferromagnetic resonance and Brillouin light scattering study. As an introduction, artificial spin ices are lithographically defined nanomagnets like this one, and they were initially created to mimic the behavior of crystalline spin ice. It was realized that the dynamics of these interacting lattices would have unique traces, and depending on the microstate of the system, like the orange colored elements in these blue ones, we get different resonance spectra like this one. Then artificial spin ice were measured using ferromagnetic resonance technique like this one, and it was seen that they had very characteristic spectra. And similarly to this work, we focus on the dynamics of our square artificial spin ice lattice, and we do angular dependent measurements. So we performed two different measurement techniques, ferromagnetic resonance spectroscopy or FMR and Brillouin light scattering spectroscopy or BLS. In the FMR setup, as you can see here, we fabricated coplanar waveguide shown in yellow on top of the silicon substrate. And then we fabricate artificial spin ice on top of a signal line of the coplanar waveguide, which is shown in gray. Then we pass the microwave current that generates an oscillating field along the y-axis or perpendicular to the signal line, which is shown with these red arrows. And we measure the transmitted signal using a vector network analyzer. To vary the inter-element interaction, we apply an in-plane biased magnetic field H, which is shown here. And at an angle theta, where theta equals 0 degrees means along the x-axis, and theta equals 90 degrees means along the y-axis. In the FMR technique, the detected resonance frequency is the most intense, or the torque generated is maximum when the magnetization is along the signal line or the x-axis. However, in the microfocus BLS setup, for thermally excited spin waves, a laser beam is shined through the sample. And using the reflected light back into the interferometer, we can measure the resonance frequency of the lattice. Here, a scanning electron micrograph of the studied square artificial spin ice, which is made of permalloy with the dimensions of the nanomagnet is shown. Along with the experimental techniques, we use micromagnetic simulation to verify the experimental results. And here's the approach. We apply a sync pulse with the amplitude By, as shown with the orange curve. And then we record the resulting onset of the magnetization dynamics MZ, which is shown in blue, which is the average Z component of the magnetization. The inset here shows MZ and By on a magnified scale in the instance of the time when By is applied, the pulse is applied, and long after that when a steady state oscillation of MZ is observed. The corresponding Fourier transform shows the eigenexcitations of the square lattice. The inset here shows the Fourier transform of the sync pulse that features a precise cutoff frequency around 50 gigahertz. We simulated artificial spin ice using a vertex and periodic boundary conditions. And by horizontal islands, I mean those elements along with theta equals 0 degrees, and vertical islands are those along with theta equals 90 degrees. And we use mu max 3 for solve the LIANG equation. Now let's take a look at our results. Here is experimentally observed broadband ferromagnetic resonance spectra at a magnetic field applied at theta equals 0 degrees, which is shown with the green arrow here. The microwave field is directed along the y-axis. The color-coded maps show the strongest microwave absorption corresponding to a minimum scattering parameter S12 in dark colors. We switch the magnetic field from negative to positive field. Okay, now the most intense mode, this one, is located in the horizontal island. Just want to explain what's going on. And around 50 millitesla, there is an asymmetric behavior, which is due to the magnetization reversal of the horizontal island. Another mode to consider is the W-shaped characteristic mode, this one, that originates from vertical islands and gets fainter around the zero field. And this is due to the fact that at zero field, the magnetization in the vertical island aligns with their easy axis or y-axis. And hence, both the vertical island magnetization and the microwave field are in the same direction. Furthermore, to change the inter-element interaction, we apply bias field at theta equals 75 degrees. Here, the most intense mode, this one, which is predominantly associated with the horizontal island dynamics, is lowered in frequency and it's mostly flat. We also see a behavior like avoided crossing at around -100 millitesla that piqued our interest. So we measured the same sample using macrofocus BLS to further investigate and confirm it. So here is when we measured the same sample using macrofocus BLS technique on thermally excited beam waves. Here is at 0 degrees applied magnetic field. Compared with the FMR technique that I showed you previously, this one, it can be seen that there are significantly more modes detectable compared with the FMR technique. In addition, there are comparable resonance intensities in horizontal and vertical islands. For example, in the FMR technique, we have like this one in the horizontal island, much more intense than the one in the vertical island. But here we don't, the intensity are comparable. We further measured the sample at 75 degrees with BLS, and here's the result. Further, to confirm the experimental results, we used micromagnetics, and here are the corresponding micromagnetic simulations at theta equals 0 degrees and theta equals 75 degrees compared with the BLS. As it can be seen, there is a remarkable agreement between simulation and microfocus BLS, which is good. And furthermore, there are mode splittings around -100 millitesla in this red box, shown in this red box, that could be interpreted as avoided crossing, where we investigated further in the, and I'm going to show you in the next slide. So I'm going to focus on this region, field and frequency region. And the beauty of the micromagnetics is that we can take a look at the 2D profiles from which we see which element dynamics are located, like this one here. And as it can be seen, before a splitting occurs at -150 millitesla, which is shown with the red curve, which corresponds to basically this graph is the 2D graph of at -150 millitesla. The main excitation mode, or the most intense one, and which is shown with the red dot, is located on the horizontal island and the edges of the vertical island. A higher order mode can also be observed at a higher frequency, but with a much smaller intensity, which is marked with a red triangle, or this one. So, however, when the magnetic field is reduced to -100 millitesla, the orange symbols, which is correspond to this orange curve here, we observed that the two modes split into 4 resonance modes. So at minus 150, we had 1, 2. At minus 100, we have 1, 2, 3, 4, or 1, 2, 3, 4. And the lowest frequency mode, which is marked with the orange dot, or this one, corresponds to the vertical island edge resonance mode. Whereas the highest frequency mode, the orange triangle here, or this one, correspond to the higher order excitation of the horizontal island. Interestingly, the modes in between, the two modes in between marked with orange star and orange cross, arise from the main mode located in the horizontal island, as you can see here. So as a result, although this could be interpreted as avoided crossing, our simulation results indicate that this splitting is just the splitting of the modes into different sublattices of the square artificial spin ice. To summarize, we showed three complementary techniques: broadband FMR, microfocus BLS, and micromagnetic simulations. We showed that the mode splitting depends on both magnetic field angle and amplitude. And based on the micromagnetic modeling results suggest that the splitting is due to the oscillations localized in different regions of a vertex of our square artificial spin ice. And finally, we showed that thermal spin wave spectrum is sufficiently strong to be detected by macrofocus BLS. Again, this work was from our recently published paper in IPL, and I want to thank the US Department of Energy for supporting and funding this work. Thanks for your attention, and if you have any questions, please let me know.
Thank you, Mojtaba, for a interesting talk. Is there any question from the audience? You can raise your hand by clicking reaction and then raise hand. Okay, if not, I have one minor question. So you showed the results from broadband FMR, BLS, and micromagnetic simulation. So BLS and micromagnetic simulation shows many branches, many different modes present. Why do you think broadband FMR don't capture those?
Well, that's a good question. So for example, one mode to consider here, you can see on the top, is not shown in the FMR. So in the FMR technique, we just excite the standing spin wave, and basically K equals to 0. And that's the nature of the microwave excitation. But in BLS, we basically excite, in this method, we basically excite the spin waves thermally. So we have a large wave vector range, and that could be detected by the microfocus lens, which has a high numerical aperture.
Okay. So for micromagnetic simulation, you also excite other than K equals 0 intentionally?
So I don't think that mode is even clear. I mean, here. So I don't think so. So I think so. In micromagnetic simulation, we see K0. And in BLS, so there are some modes unaccessible in FMR, and probably even not in the, so this is like the logarithmic scale plot for the micromagnetics, but it's still not visible there.
Okay, thank you.
Sure, no problem.
If there is no other question, we'll move to the next talk. And for the next talk, we have our new moderators are joining. Sam would be our Sam
sorry,
will
yes.
be our moderator, and Jian will be helping him.
All right. Actually, Jian will be the main moderator. So
okay, no worries.
Hand the
Jian
time
will be
over
the
to
main
her.
moderator. Okay.
Thanks, Ima. Thanks, Nima. Now the session is switched back to Asia Pacific region, and the first talk is given by Jian MASELL from Riken in Japan. His talk title is Moving Skyrmions with a Small Thermal Gradient. And Jian, I'll inform you after 12 minutes. And yeah, so mind your time. And now the floor is yours.
I think you're still muted.
Oh, okay, I see.
There you go.
Thank you very much. Yeah, I accidentally muted myself again and couldn't unmute again. Okay, thank you. Yeah, let me share screen and show you my presentation first of all. Okay, there it is. I hope you can see it, everybody. I would like to talk about how to move skyrmions in small thermal gradients. And I should have added in insulators, in magnetic insulators. And this is work done at Riken. I'm a JSPS here and Humboldt postdoc in the group of Naoto Nagaosa, doing theory, but I'm working a lot together with experimentalists, like, for example, Wu Sensei, Zhujian Wu, and she is doing LTEM. And so we combine various techniques here at Riken, like the LTEMs by the group of Wu and my simulations to gain nice results like these moving skyrmions in small temperature gradients. And this has just been published on Monday, actually, in Nature Communications. Okay, that's my title image here. And I don't only have a title image, but while I composed this presentation for you, I always had this tune in my head, this auto tune. And if you like to listen to American pop music in the late 2000s, you probably know the song, but I'm not allowed to play it here, of course, because of copyright reasons. But so this one keeps going in my head, and that's also a short summary, if you like, to take home, because it's about a hot side and a cold side, which is yes and which can be no, where you can go in and you can go out and you move up or you move down, depending on where you go. It was part of a presentation by Katy Perry and other people from 2008. If you know the song, you can take it home as an earwig, like me, and keep it for weeks long. Maybe you still remember some of the contents of the presentation. That would be nice. All right. These are my two summaries, if you like, for the talk. Skyrmions can be moved in thermal gradients. And these 4 lines of the song already tell you all the important information. We will see later how that goes. But first of all, skyrmions. There have been a couple of talks already during the last 26 almost hours on skyrmions. So my short introduction on skyrmions would be this projection movie. I hope you can see it in your bandwidth, and my bandwidth is high enough. We can project from the hedgehog ball, from the hairy ball, down to the 2-dimensional plane via stereographic projection, and thereby the final object, the skyrmion down here, still keeps the topological features of the hairy ball from the very beginning. But that is in 2D. In 3D, the skyrmion would continue like a string, like you can see it here, this pixelated graph on the right side. And that is something that we looked at, for example, in the past. Now, let me use the first minute as a cheap advertisement for our previous works. For example, where we measured the zoo of defects in skyrmions. So one of the nice features of skyrmions is this topological protection kind of feature. But that still means, well, that doesn't prohibit skyrmions to be annihilated at some point. So you can have defects inside skyrmions, which are then truly topological defects, like the Bloch points here, very tiny, blue and red, where you break a skyrmion tube, or you can fuse skyrmion tubes, or you can just allow them to bend quickly and exit through a surface. And this is something that we simulated here with micromagnetics, and that we also measured in experiments. And if you then have a side view on these skyrmion tubes, you can identify in Lorentz transmission electron microscopy all these spaghetti here and the different defects in the spaghetti. And by comparing the LTEM graphs to the simulated graphs here on the right side, you can identify and distinguish the different types of topological defects, like this trouser fusing defect and the Ober kind of defect where the skyrmion suddenly ends, and the exiting skyrmion. And I presented a poster. I may also still present the poster if you like, if you want to come there. Poster B1, that's my avatar there, looks exactly like me with a mask. This is also the place where you will meet me after this talk. If you have any further questions or questions on this one here with anti-skyrmions in S4 magnets, the very first discovery of anti-skyrmions in S4 symmetric magnets. Very interesting topics, plus surface domain walls, also very interesting. I recommend you to join. And another nice thing that we did, for example, last year was together with Max, who gave a presentation yesterday at about the same time. And then we measured, for example, the topological Nernst effect in skyrmion lattices. So Nernst effect would be you have a hot side and a cold side, and your conduction electrons are happy to move from the hot side to the cold side. So they fly over the skyrmion lattice, get deflected to one side, and then you can measure a voltage here, a perpendicular voltage on your sample. And for the details, I suggest you look at Max's talk. I think that's been recorded on YouTube, so you can watch it or ask Max. He knows the details. And now back to temperature gradients. Let's start with the simulation, because I'm a theory guy. I like to do simulations. And if you have a thin slab of some insulating magnetic material, then your skyrmion may look like this. So there's some slight distortion because of surface effects. And the thermal gradient here is hot on this side and cold on that side. And then what will happen is, hope you all can see it, it moves to the top left side. Wonderful. So these simulations are done with Mumax free, not with the upgraded version that we're using for many other projects, but with the normal version. And it's exactly like it was predicted in 2008 by Perry et al., that it moves from hot to hot from cold, where it is the yes region, and this here is the no region, right? So it moves into this edge here, out of this edge there, and they even predicted correctly the Hall effect, because it moves up while going there, where it's down on this side here. Wonderful. So everything was in principle already known in 2008. We just did not understand it because it was so very critical. But then there were also other simulations in 2013. For example, these ones here by Gong and Jian, which showed exactly the same things that we just saw in the simulation. Other papers here, for example, by the Los Alamos people from 2014, and a bunch of other papers from that time, all saw this effect, and also some experiments which measured it indirectly, because they did again shine a beam, an electron beam on a sample, which gives you a radial thermal gradient, and then in this radial thermal gradient, the skyrmion lattice starts to rotate. And that can be interpreted as this kind of moving skyrmions in the thermal gradient story, but it's indirect because they are now moving, they're now rotating, they're not moving along the thermal gradient. Okay, and if you want to do some analytics, you can also look at this paper here by Kong and Zhang, the first one. Then you can write down your equation of motion for the magnetics. You can integrate out the fast oscillating degrees of freedom, arrive with a collective coordinate teletype equation of motion for the skyrmions, where the most important part is actually this one here, this first term in the Vx, which is the effective Magnon current, which incorporates the effective Magnon current. Then you have to calculate the Magnon current via some variation of the Bose-Einstein distribution, which looks like this. You can calculate the effective Magnon current, but in their paper, unfortunately, they used a linear dispersion for the skyrmion lattice. And now we know that was a typo that they took from another paper, unfortunately. So a little later, 1 year later, there was Kovalev's paper, where he included the non-adiabatic beta type correction to this equation of motion, and derived it also from integrating out the fast oscillating degrees of freedom. So his equation of motion is a bit more sophisticated and includes this beta, which is pretty much 1.5 times alpha. And he also uses the correct dispersion for the ferromagnet. So now we're considering isolated skyrmions in the ferromagnetic background. And what he could do was to boil this all down to this one integral, dimensionless integral that has to be solved, and gives you the results, the Magnon current in 2D and in 3D. And a thin slab, which is of the order of one skyrmion size thick, which is what we usually have in experiment, that is already in the 3D limit. So we look at this one here, but unfortunately the dispersion that he used was for the 2D case, not for the 3D case. So we corrected this. In 3D, it looks like this. You need this extra term here, which gives you an extra contribution along the external magnetic field if you have a field polarized phase. Then this F not integral does this, so it has this square root type shape close to the transition from ferromagnetic to conical background phase. That gives you an additional speed up close to the conical phase or inside the conical phase even. And because of the speed up, you can calculate that the velocity of the skyrmions, in, for example, copper oxide selenide at 20 kelvins would be 1.6 times units instead of 0.7. I mean, that's not a huge difference, but it's a factor of 2. And so what my colleagues did experimentally then is to take copper oxide selenide, which is a skyrmion hosting magnetic insulator, cut that into a thin nanostructure with some thickness here, 0.1 nanometers there on the fixed side, lay that on top of some holder, glue platinum wires on there, which can be used as the heater. And then there's the observation area, which is this super thin area here, 100 nanometers thick. The skyrmions in here are 60 nanometers diameter. So we are in this 3D limit, if you like, from the theory before. This is then the view area for ATOM. And then, for example, we can remeasure the phase diagram for this thin slab and then see that we have a stable skyrmion lattice phase. Plus, we have a phase transition in here from skyrmion lattice to isolated skyrmions with conical and to ferromagnetic. And this here is the area where we want to look at things, because there we have an almost polarized background or a conical background with isolated skyrmions or skyrmion clusters. And those we can trace with our experiments. So the experiments then look like this, or the movie that was taken during the experiment looks like this. There it goes. And now it rips off in the end. So it's very non-linear motion, if you like. There's first this first part that separates, and this entire skyrmion cluster elongates, and then after some time it starts to rip off finally. So there's one snapshot where you can see the border of this skyrmion crystal to polarized magnet being here, and then at another snapshot at some later time it is here. And from these snapshots, or from the whole movie, you can then extract the average velocity of this skyrmion frontier and the Hall angle. Or you can look at skyrmion clusters moving inside this conical or polarized background and see that they are rotating while moving, for example, or they can merge if one of them is pinned. So the right one here should be pinned and the left one can move and then merge with the right one. And it's all as in the prediction by Perry, that it moves from hot to cold. Wonderful. But these are the statistics, if you like. So the velocity shown in red here is 0 at some low thermal gradient. And at some point you can unpin the skyrmion lattice. And then it does this quite characteristic unpinning type of transition, which in this logarithmic linear plot here should look like, follow my laser pointer, should theoretically look something like here. We have this kind of slope, and then it goes up exponentially. So you can say, this data fits nicely with theoretical prediction because it measures the shape that we expected for pinned and then unpinned skyrmion lattice. But if you compare numbers, you will find that theory predicts you for this value here, for example, a velocity of 8 micrometers per second, whereas the experiment give you a factor 10 less. But I think that's okay because we are still in the strong pinning and strong creep regime here. That's it. With this, I would like to thank you for your attention and all my collaborators for the nice collaborations. Take home the song, listen to it again if you like, and don't get rid of the earwig again, and my family for their support here at home. Thank you very much.
Thank you for your very nice talk. And now the floor is open for questions. So if you have any questions, you can raise your hands by using the reactions tab in the lower window.
Maybe I can start us off. Thank you for the talk.
Waiting for, yeah.
Oh, sorry. Yeah. So if you have a question, please put up your hand. But I'll start us off. Great talk. Thank you for putting that song back into my head. Yeah. That's a very interesting project, and I look forward to reading the paper. Can I just ask, because you have a thermal gradient what is the actual temperature of the sampling area? Does that change over time? Because like if you heat one side, over time, won't that form a thermal equilibrium of the whole sample? So is it at 20 Kelvin that whole time? Is it an active cooling? I just wanted to ask, yeah, what is it that, what is
our cooling or our cold bath is this huge silicon block here on this side, which is connected via silver to the sample. So this block here is huge, huge, huge compared to the sample. So that's why we expect that during this 1 second long experiment, there's not much equilibration going on here, such that this cold side would really heat up.
Oh, I see. Yeah. So like it should be, so it is in thermal equilibrium in the sense that the temperature doesn't shift.
Right. That's what we expect. Yeah. Because this side here is connected to a very huge cold bath, and that side here has the heater on top only, and is disconnected here via something that is non-heat transmitting. Yeah. And so we expect that this is indeed our equilibrium condition with the equilibrium thermal gradient here.
I see. Thank you.
Okay, are there any other questions? Okay, I have one quick question. Compared to the Skyrmion velocity driven by electrical sources, how many the numbers do you know about the Skyrmion velocity in the electrically driven one and the thermally driven one?
Well, that depends on the thermal gradient, of course, because he would try to look at the deepening transition, and actually forgot what the Skyrmion velocity was in other experiments where they measured it at the deepening transition via electric currents, but that then also depends on what kind of defects you have in your system, what the defect density is, how large your Skyrmions are, and so on and so forth. But this is more to be seen as a proof of principle. You can do it in an insulator, and it seems that the velocity can go up pretty high here. And now I would encourage people who are more on the technical application side to look at how fast you can actually drive them with the thermal gradient, because I would believe that at some point this breaks down, just because you cannot make a thermal gradient as large as you like. At some point you will hit the critical temperature on some side.
Yeah.
So at some point this has to break down at some point.
Okay, there's another question. Zulfidin? Yeah.
Thank you for the talk. I have a quick question. I'm not really familiar with this, so I just want to know, how did you grow the sample, and how do you know if there is Skyrmion on the sample without imaging first? Is there a way?
Well, the sample is grown as a single crystal, and then you cut via FIB, you cut this thin plate and you do the nanostructuring, or my experimental colleagues do the nanostructuring. And yeah, cut this nanostructure down here, you can see there, from this crystal, and then put it on top of this holder, the silicon holder. And we know that there are Skyrmions inside already because, well, the phase diagram of copper oxide selenide biocrystals is well studied, and then we know that as we go to thin samples, the Skyrmion lattice phase will populate more space in the phase diagram. They become more stable in thin plates. And to prove this, we actually measured this phase diagram for the thin plate part of our sample. And there we see these Skyrmion lattices. Then we can say, by measuring the phase diagram, where we should position ourselves here in this temperature magnetic field phase diagram to see isolated Skyrmions or Skyrmion clusters inside a conical or polarized background. I hope that answered your question.
Thank you. Thank you for that.
Okay, now it's time to move on to the next talk. So the next talk is given by Bryce MULLENS from the University of Sydney in Australia. His talk is Structural and Magnetic Studies of the Layered Perovskite, a combined experimental and computational study. Okay, Bryce?
Wonderful. Thank you very much for that
Now
kind
we can start.
introduction.
Yeah.
Thank you so much. So hi everybody, my name is Bryce. I'm a PhD student at the School of Chemistry at the University of Sydney. And today I'm going to be presenting just a short excerpt on a study that we're currently doing on the structural and magnetic studies of a layered perovskite, cesium manganese fluoride, or CSMnF4. So before I get started, I'd just like to give a quick thank you to my supervisors, to ANZI and ANSTO for our funding, as well as our the beamline scientists that we've used at the Australian Synchrotron, at the Australian Centre of Neutron Scattering. Also to all of the organisers for AtC-AtG Magnetics. I understand it's the end of the conference now, and it's been wonderful. It's been a privilege to be a part of this. So to kind of kick things off today, I wanted to start off by talking about these generalised AbX4 structures, which I've kind of highlighted over here on the left-hand side. So the reason why these are important is because we can put all different sorts of anions and cations into them in order to observe how that changes their structure. So if we take our periodic table on the right-hand side here, our A site, we usually put in a group 1 metal, things like sodium, potassium, rubidium, and cesium. And then we can see that our B site forms these what we call layered perovskites. They're essentially all connected octahedra. And these can tilt in and out of plane. We can get all sorts of different symmetric distortions depending on what sort of metal we actually have in there. So things like manganese, iron, zinc, these are all very common. On our anion site, it's a little bit less creative. We're usually looking at either oxygen, fluorine, or chlorine, even though chlorine's a little bit too big. What's important about this is that we can change our Jahn-Teller distortion based on the strength of our on our anionic or spectroscopic ligand. The reason why this is so important is because if we take two samples like how I have done here, so on the left we've got cesium iron fluoride, and on our right we've got cesium manganese fluoride, we can see that these two samples are isostructural. They have the exact same symmetry. The only thing that's different is that we have a different transition metal on our B site. If we were to unpack the polyhedra, like how I have done down the bottom here, the actual magnetic exchange between these two transition metals is governed by the actual bond angle. And we can see even though we have a slight difference in bond angle between these two, we get a completely different magnetic ordering as a result. Our iron sample is antiferromagnetic, whereas our manganese sample is ferromagnetic. We can also see this by changing the A site. If we change cesium for something like rubidium in rubidium manganese fluoride, this also changes our ordering. And this is really important because it kind of gives us a rich framework in which we can explore two-dimensional magnetism, which is really important for things like topological materials, and it's also great for potential applications in spintronic devices, which I'll get into right at the end. So what I've done is I've separated my talk today kind of into two different parts. So our computational work, which was done by our collaborators in the University of Hyderabad in India, where we look at what causes this ferromagnetism or antiferromagnetism to arise. And then we've also done some experimental work on going forward and synthesizing these compounds to see how difficult they can be to do. So first of all, I'm going to focus on our computational work. This was done in collaboration with Dr. Kanchana in the University of Hyderabad. They were able to perform DFT calculations on these structures in order to figure out what sorts of interactions are at play. So I've got our ground state electron density maps here on the left-hand side. And we can see just by looking down particular crystallographic positions, we can see how these electrons are actually distributed. And in turn, how we can see these sorts of super exchange effects that take place in this crystal structure. So we can see there's a large electron density along each of our perovskite layers, which I've highlighted here in our gold box. That shows that our magnetic ordering is confined just to within the planes of these perovskite layers. Moving on to a different crystallographic position, we can see that there's no electron density between the cesium and things like the manganese or the fluorine. So this means that these are purely ionic bonds. They're not engaging in the kind of super exchange mechanisms at all. All of these mechanisms are purely confined to the two-dimensional planes of our perovskites themselves. Moving on from this, Dr. Kanchana was able to determine how the actual orbital mixing of these manganese and our fluorines can actually lead to the different sorts of interactions. And what we can see here is that we can accurately reproduce the fact that it is in fact a ferromagnet by looking at the d orbitals of the manganese in its high spin state, and it's mixing with the p orbitals of our fluorine. However, what was surprising was that we could actually recover this antiferromagnetic ordering at a higher pressure, so at something like 3 gigapascals. When we do this, our bond angle between our transition metal and our fluorine changes, which causes a more favorable interaction with our orbitals, which causes it to align antiferromagnetically as opposed to ferromagnetically. This study also allowed us to predict the Curie temperature of these things, which is around about 18 to 19 Kelvin. So with all of this in mind, we wanted to then go forward and see if we could match our computational work with some experimental work. So we wanted to try and synthesize these layered perovskites, and this was put on me, this was my job. The problem with this is that a lot of the literature with these structures dates back to about the late 70s, and this hasn't been updated for quite some time. What's more on this is that if we were to look at the experimental methods that are actually in these sorts of papers, we see that it involves dissolving manganese 3 oxide in something like 20% hydrofluoric acid. So if anybody's unaware with hydrofluoric acid, it is both corrosive and toxic, and it's fatal upon both contact and upon inhalation as well. So of course we wanted to give this a go. We wanted to see if we could synthesize it using hydrofluoric acid. And we did it using a simple co-precipitation method. Basically, we dissolved both cesium fluoride and manganese oxide in a small solution of hydrofluoric acid. We then mixed these two together and we allowed them to stand for about 24 to 48 hours. And what we saw was that we got these really nice, beautiful cesium manganese fluoride crystals that came out of our solution. So we were able to filter these off, we were able to wash it with methanol, and we did some X-ray diffraction on them. At least we thought we had beautiful crystals. That's not exactly what we saw. We've got our X-ray diffraction pattern here, and you can see fitting it using the Rietveld method, we have a whole bunch of unidentified peaks, which is not particularly great. It meant that the crystals that we were actually getting out of this weren't 100% pure. We had things like manganese oxide left over as an impurity. The cesium fluoride was fine. We didn't find any of that, but we had these two different cesium manganese fluoride structures that we're able to form. So the first one was the one that we wanted, but it was only about 49% phase pure. And then at the bottom, we can see we have this other hydrated phase, which causes all of our octahedra layers to kind of separate and split up, which will reduce any sort of magnetic ordering that we could see. So what we did was we wanted to tweak this synthesis a little bit, knowing that the last time that it had essentially been done was back in the late 70s. And we wanted to see if we could remove this hydration from our samples at all. So what we did was we used a cesium fluoride excess because we knew that we had manganese oxide left over. And we also added an extra heating step. So we thought that if there was water in our sample, we could remove it, we could dehydrate our sample by leaving it about 200 degrees for about 4 hours. And then what we could see is that we were able to recover our pure cesium manganese fluoride phase. We took these crystals after we synthesized them a few more times, and we can see we get a gorgeous X-ray diffraction pattern as a result. All of our peaks are indexed here. We get nice matching up with all of our intensities with our Rietveld refinement. We can also see even at high angles, we don't have any of those kind of nasty peaks that are unindexed, which means that we don't have any of that manganese oxide or anything left over, which was what we wanted to see. So we've been able to synthesize these crystals. We can do it on the bulk now, which is fantastic. So moving on for the future work of this, we wanted, put them in our PPMS instrument so we could measure this kind of ferromagnetic or antiferromagnetic ordering at low temperatures. And we also want to do neutron diffraction studies on them at the Australian Centre of Neutron Scattering. What we can do is we can take it below its Curie temperature where we get that ferromagnetic ordering, and we can do things like index the magnetic peaks in order to get an idea of how these spins are arranging themselves on this structure. Our neutron diffractometer is named the Wombat after an Australian native animal down the bottom here, which is a nice little cuddly fellow. So moving on from this, we wanted to do it on the PPMS, which we were able to do. The PPMS at the University of Sydney is capable of going as low as 1.8 Kelvin. So we did both a field cooled and a zero field cooled run. We can see we get this kind of little inflection in our magnetic moment. and that occurs at about 18 Kelvin. So that matches up with our computational studies. We're able to get a ferromagnetic ordering at below 18 degrees Kelvin. We've also got our Curie-Weiss fit on the top right-hand corner here as well. We then took it and we did some magnetic field sweeps. And we can see at 1.8 Kelvin, we get this opening of our hysteresis plot here, which means that we're observing that ferromagnetic ordering, we're observing that residual magnetism at zero field. When we heat it above that temperature, so when we did it at 20 Kelvin, you can see we don't have that opening of the hysteresis, which means that we've got a pure sample of our cesium manganese fluoride, and we're able to reproduce our computational studies as well, which is quite nice. So that brings me to my conclusions. What have we actually done in this project so far? First of all, we looked at why cesium manganese fluoride is of potential interest. It is a 2D topological magnetic material. And we could see that whether we have either manganese or iron, or whether we have cesium or rubidium, we get completely different magnetic ordering as a result. With our computational studies, we looked at ground state DFT calculations to see that all of our magnetism was confined within the planes of the perovskites themselves. There was no kind of interaction between the cesium atom and the perovskite layers. We were able to synthesize this with very high purity using a simple co-precipitation method. And then we were also able to measure the hysteresis loops of these, which we could observe at below 20 Kelvin. So I'll pop my email down the bottom there. That's all from me. Thank you very much for listening. And I hope to see a lot of you in Gathertown after this.
Thank you for a nice talk. Now the floor is open for questions. You can raise your hand using reactions. Okay, Martin, there is a question in the chat box. Martin, you can unmute yourself.
Yes, do you hear me?
Yes.
Oh. Unmuted again. Okay, now you can do it.
Yeah, so you've shown the electron density distribution from computational calculations, but how would this compare to the actual measurements from diffraction experiments of single crystals?
Yeah, that's a great question. We haven't actually done any single crystal work with this yet. So we've managed to synthesize a whole bunch of crystals, but we haven't yet got one that's of an appropriate size to do single crystal diffraction or anything like that. That's certainly what we're trying to do. We're still trying to tweak this extremely nasty synthesis that we're trying to do, but that's certainly on the horizon. We would love to do a proper comparison between these two.
Okay, cool. Thank you.
Thanks, Martin.
Okay. Are there any other questions? If not, let's thank the speaker again. And Bryce, you can move to Gathertown to have further discussion with the audience.
Thanks, everyone.
Now we move on to the next talk. And next talk is given by Jian Liang from the Southeast University of China. And the title of talk is Anisotropic Magneto-resistance in 2D van der Waals nanoflakes of iron materialite. Okay, John, you can now share your screen.
Okay. Can you flip your video as well? You're upside down at the moment.
Video? Which one?
Your video screen. Doesn't matter. It's all right.
Sorry, I can't.
Doesn't matter. It's all right. It's all right.
Okay.
We can see your slides.
Yeah. Okay. Good morning, everyone. I'm from Southeast University in China. I'm glad to join this meeting. I would like to thank this conference organizers for giving me this opportunity to introduce my work today. Today, I'm going to talk about electric transport in 2D van der Waals ferromagnetic FGT. In recent years, it has been absorbed a lot of attention in area of spintronics. My presentation topic is Anisotropic Magneto-resistance in 2D van der Waals nano-flakes of FGT. A ratio of element for composition is 3 to 1.2. There are 3 parts of my presentation. And the first part is research background, second part is research progress. The most important part is the result of magneto transport measurement. At the last, I will summarize all my work and show possibility of the future work. Moore has proposed a law. It says that the number of translators per unit area doubles every 18 months. However, as the translators get smaller, it will reach a physical limit when the width of the channel is less than a certain value. The function of the translators is disabled as a turning effect occurs. To solve this problem, researchers have come up with a number of ways, such as using nanosheet or nanowire to reduce the size of the material and making the FET into the vertical structure. But one of the most promising cases is to replace the traditional semiconductor materials with 2D material of atomic thickness level. As shown in last picture, compared with the thin FET and the 2D material-based FET devices further reduced the size of the device. Moreover, 2D materials have the advantage of small value, low power consumption, and the high performance. A few decades ago, Vermi and Vagla together calculation predict that there is a low long-range ferromagnetic order in 2D system. Physicists have debated this question for decades. When long-range magnetic order was discovered in monolayer of chromium chlorine, and that broken their theory, many intrinsic 2D magnets have been discovered in recent years with different properties, including conductors, semiconductors, and insulators. In spintronics, we focused on the Curie temperature, saturation, magnetization, coercive force, and scalability. And FGT has advantages in these areas. In research of spintronics, the key point is that FGT has good electrical conductivity, and it has strong out-of-plane magnetic anisotropy and is hard magnetic metal. The coercive force can reach 5,000 and 500 Oster in nanoflake. In bulk FGT, the Curie temperature is 230 Kelvin. In monolayer, it can reach the 130 Kelvin. Besides, it is reported in nature that by gate turnable, the Curie temperature is regulated to above room temperature. A lot of excellent work works based on FGT devices have been done, like MTJ or spin wave with HBN and graphene, SOT effects in the heterostructure with PT. More work is about the basic magnetic research and regulation. However, the research on its magnetic resistance is seldom to see. First, we prepare the FGD bulk crystal by using CVT technique, but the bulk crystal size is up to 6 nanometers. The size of bulk crystal is very important for next mechanical exfoliation. We can obtain large area thin layer if the bulk crystal is large enough. It can be seen from the SEM image. that the bark crystal is regular hexagon in shape, and it's consistent with its crystal structure. Also, the layered structure can be seen. We use EDS to get the composition of is most 3 to 1.2. The crystal structure is mirrored by XRD. The crystal orientation is 0, 1, 2. It is typical 2D crystalline. After mechanical exfoliation, the flake with different thickness is obtained include a few to 10 nanometers, and the character is similar as the background, which means we don't, after mechanical exfoliation, we don't break the crystal structure. And then let us look at this picture. I will introduce the technique on the mechanical exfoliation and the progress of device fabrication. For getting large area 2D thin layer, we use the titanium and gold assisted exfoliation method. This method is reported to have advantage on the FGT exfoliation. Should be noticed that the total thickness of titanium and the gold layer need to be thinner than 4 nanometers because there is low influence for our magneto transport measurement because it's insulated. After exfoliation, the figure shows that we obtain large area thin layer of couple of 100 micrometers. Okay, let us see the magnetic properties result of MT measurement by squid indicates that out-of-plane magnetization is larger than in-plane for bulk sample, indicating that the easy magnetization axis is along out-of-plane direction, and the Curie temperature is obtained at about 220 Kelvin. For the individual nanoflake, AtC curve was mirrored, and the Curie temperature is determined as 119 Kelvin. At 20 Kelvin, about 20 Kelvin, the resistance reaches minimum value, which is reported to be explained by Kondo effect. At the temperature lower than Curie temperature, the resistance increases with the increasing temperature. It can be fit by the formula. By fitting the coefficients A and the B are obtained, we find that the 3-second power term of T predominates, indicating that the interaction between conduction electrons and the localized spin could not be simply treated as a small perturbation represented by the square of T law for an itinerant ferromagnetic system. And the strong electron correction should be considered, such as scattering of spin wave excited by KT. Let us see the anomalous Hall measurement. From the Hall loop, we further confirm that the easy axis is along out-of-plane direction of the flake. In the previous report, the Hall resistance decreases with the increasing temperature. However, in our work, it is found that the largest Hall resistance is at 50 Kelvin instead of 5 Kelvin. Based on the formula of Hall resistance, it consists of 2 parts, normal Hall resistance and anomalous Hall resistance. The coefficients of anomalous Hall resistance is related to longitudinal resistance, the Rx6. So we can see that it's influenced by the Kondo effect. We also mirrored the RXY with the change orientation of a magnetic field from the UUC axis to the AB plane. We found that all the curves are well fit with a sine function. Next, we go to the memory measurement. It is the magnetic transport properties for the voltage detected in the current direction. We see that there is a jump. There is jump of the resistance near the zero field. When the magnetic field is perpendicular to the current plane, by analysis, we found it is because a small angle phi and between the current and the voltage directions still remain. Corresponding to the small part of the contribution of anomalous Hall effect. After removing the component of anomalous Hall effect, we obtained the typical RxH curve. As we can see, Rx increases with increasing temperature and decreases with the increasing magnetic field for both current parallel or perpendicular to the magnetic field. The resistance Rx of current perpendicular to the field is always larger than the current parallel to the field one, indicating negative anisotropic magneto-resistance. Such an anisotropy is disappeared until 190 Kelvin, just agree with the Curie temperature. It is interesting to note that the largest difference between Rx perpendicular and Rx parallel is at 50 Kelvin instead of 5 Kelvin, which is, we think, due to Kondo effect. Here, we show the angular dependence of the resistance with magnetic field 8 Tesla. From experiment data, we see that the amplitude for oscillation of Rx with theta is not symmetrical. It is larger when theta near 19 degree than 0 degree. Due to the angle phi mentioned above, we use this formula to fit all the curves very well. The first term, R1, is the typical anisotropic magnetic resistance expression, and the R2 term comes from anomalous Hall effect component and shows the relationship of sign function. By fitting the angle dependence of resistance and the component of anomalous Hall effect are separated. By fitting the angle dependence of resistance, we obtain the ratio of AMR value. It reaches a max value of 1% at 50 Kelvin, which we suspect is related to the Kondo effect about it, but further study is necessary. In the last, I think there are some other points that we need to study further. The FGT Nano-flakes is necessary to study to see its property given monolayer. How about the angle dependence of Rx in the flake plane? How to increase FGT anisotropic magneto-resistance may be done by interface or get tuned. How about the tunable properties by using magnetic processing effects such as the heterostructure with 3D magneto-metal or LOI and FGT. Okay, thank you for your attention.
Thank you, Jian, for your wonderful talk. And now the floor is open for questions.
Okay. Wei Jian, you should be able to unmute.
Yeah.
Yep.
Hey. Well, hello, Dr. Liang.
Hi.
Why? Well, thank you for your talk. And may I ask you a little question?
Yes.
Please turn to the page about your magneto-resistance.
This one?
Yeah. This slide, please.
Okay.
I see the results of your magneto-resistance. All the results are negative, right?
Yes.
I'm not very understand this result, can you explain it?
Okay, thank you for your good question. In the 2D system, it's like our TMR model is like a sandwich. It it has been reported that in FGT, antiferromagnetic phase exists. In 2D system, it's like a sandwich system at FM, long FM and FM. So we think it the MR it will like TMR, but the value is so small than TMR. But from now, we just can explain it by this opinion.
Okay, so it's the TMR, right?
Yes.
Okay, okay, thank you. Thank you very much.
Okay.
There's another question in the chat box.
Yeah.
Can you hear me now? Hi.
Yes.
Thank you, Professor Liang. And I have a question about your full resistance loop. Can you take the slides to your RXY loop? And in previous research, I have a lot of previous research get the maximum value at 5 Kelvin, but why is the maximum value measured at 50 Kelvin in your whole loop?
Okay, thank you. Like I say, the Hall resistance is made up by the normal and anomalous Hall resistance. And the term of anomalous Hall resistance is related to the longitudinal resistance, Rx6. From the this picture, RT curve, it reaches minimum not at 5 Kelvin due to Kondo effect. So the RXY reaches maximum not at 5 Kelvin. It's at 50 Kelvin. Maybe it's at 20 Kelvin, but our Hall resistance loop doesn't mirror the 20 Kelvin. So it's like 50 Kelvin. It's the maximum.
Thanks a lot. I got it. Thanks.
Okay.
Okay. Any other questions?
Can I ask a quick question? Thank
Yeah,
you for your
sure.
excellent talk. Just out of curiosity, do you know how many layers your material is once you exfoliate it?
That's simple. It's about 60 nanometers is 6 nanometers. Yes.
Okay, so yeah, so it's still quite multi-layer for a single, so it's not a single layer yet. Okay, that's interesting.
Yeah, single layer is too hard to get.
Yeah, no, that's understandable, but very interesting results. Thank you for that. In your next slide, in slide 8, I just want to have I was a bit confused. So in the plot on top and the plot in plot C, why are they different? Yeah, so you can see that the
C and the C, you see there is a jump and there's a field. Because there's jump is because is and the I direction and the current direction and the voltage direction is not the phi is not 0. So we see this jump is come from the anomalous Hall effect. You see,
I see. And then so in C they're the same. There's same direction, right? There's no angle. Okay, understand that. Thank you.
Yes.
Okay, thank you again, Jian.